In this video, I'm going to cover section 2.1, 2, and 3. So, in section 1.2, 2.1 through 2.3, we're going to learn the basic terminologies used in probability and statistics, and we understand them, and then we see the examples. So, we just go through the textbook and to figure out that. Okay, so here's the 2.1. 2.1 is introduce the sample space as an event. So we're gonna so what's a sample space in an event? So event, see, let's see, to understand that, let's see on the examples. So let's read the first paragraph in 2.1. So if we measure the current in a thin copper wire, we are conducting an experiment. So however, day-to-day repetitions of the measurement, they can differ slightly because of small variations in variables that are not controlled in our experiment, including changes in ambient temperatures and slight variation in the gas and small impurities in the chemical composition of the wire. So and then the current source drift. So consequently, this experiment, as well as many we conduct, is said to have a random component. In some cases, the random variations are small enough relative to our experimental goals that they can be ignored. However, no matter how carefully our experiment is designed and conducted, the variation is almost always present, and its magnitude can be large enough that the important conclusions from our experiment are not obvious. In these cases, the method presented in this book for modeling and analyzing experimental research are quite very valuable. So now, see, as you can see that for each experiment, we're gonna have different result, slightly different result, different outcomes. Okay, so in the sense of statistic, we the that kind of experiment, pretty much all of the experiment called the random experiment, because I told you an experiment that can result in different outcomes even though it is repeated in the same manner every time. So see that random experiment, a definition of that terminology right there. Okay, so the simple the example is what, when you're just rolling a die, then you can have different result, right? Or you just tossing a coin, you can get different result. So yeah, this is called the random experiment. Okay, so now then, the now next one, sample space. So for each random experiment, we're gonna have different outcomes, right? So the set of all the possible outcomes are called the sample space. So you see sample space, definition sample space is in the right there in the textbook. The set of all possible outcomes of random experiment is called the sample space of the experiment. The sample space is denoted by as capital letter S. So capital letter S is denoted by sample space. Now see example 2.1. Consider an experiment that select a cell phone camera and record the recycle time of flash, the time taken to ready the camera for another flash. The possible values for this time depends on the resolution of the timer and on the minimum and maximum recycle times. However, because the time is positive, it is convenient to define the sample space as simple the positive real line. It makes sense because time is positive, so negative 1 second, negative 2 minute, it doesn't make sense in this example. So the sample space, which is the set of all possible outcomes, going to be the set of all of possible positive real number. So that's the sample space. So we define the sample space as like this. And if it is now known that all recycle time are between 1.5 and 5 seconds, then yeah, sample space can be reduced as just in the line segment between 1.5 and 5, right? And then sometimes the outcome is going to be not numerical, the categorical. It means that outcomes going to be not just not a number, but the level or some the class. So see here, If the objective of the analysis is to consider only whether the recycle time is low, medium, high, you see that here? So the sample space can be taken to be set of three outcomes, low, medium, high. And then if the objective is only to evaluate whether or not a particular the camera conforms to a minimum recycle time specification, the sample space can be simplified to set of two outcomes. So you see, yes or no. Okay, so minimum what? So it's from the we're gonna only evaluate whether or not particular camera conform to minimum cycle time specification. So is that conform a minimum cycle time specification? Yes or no. So we have only two outcomes, right? Now the next one, discrete in continuous sample space. I told you the outcomes can be classified as numerical and then categorical. The other way to distinguish the type of sample space is discrete or continuous. Discrete means that the possible outcome is the consists of the finite numbers. It's countable finite numbers. So if a sample space is discrete if it consists of finite or countable infinite set of outcomes. For example, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Or yes or no. Or as you can see, the low, medium, high, or the big or small, or the like this. And then continuous, a sample space is continuous means that if it contains an integer set of real numbers, okay, the integer in the real number line, okay, is called continuous. So let's see, yeah, so we see that in that sample space is what this is a continuous, right? Now this is the continuous, but that is what this is the discrete, and this is a discrete, right? So now this is example 2.2. So some of them. So you see that this is discrete, right? So now let's see. Now next one. Yeah. So here, this one, the sample space defined by the part set apart to real number times the set apart to real number. So therefore, this is a two-dimensional space. But anyway, this is the continuous, right? And this is discrete, and then this is discrete. This is this you see discrete, right? Okay. So because this is the not there's no infinitely countably infinite the outcomes in the sample space. So this is discrete. Okay. So now give me a second. Yeah, discrete. Yes. Now let's see. Example 2.3. Yeah, let me skip that example. Okay. So but please look at the example 2.3 by yourself. All right. So now next one. The event. Often we are interested in a collection of rated outcomes from random experiment. So, for example, we're just tossing not tossing, just a drawing a die, okay, dice. So now then what we can expect that what possible outcome going to be 1 through the 6, or 1, 2, 3, 4, 5, 6. But we want to figure out how many we want to interested in the outcomes even number. So 2, 4, 6. Okay, then the set of that possible outcomes we are interested, that is called the event. So often we're interested in a collection of rated outcomes from a random experiment. Rated outcomes can be described by subset of sample space. So keep in mind this, event is a subset of sample space. So event is a subset of sample space of random experiments, especially event is subset sample space, especially event is set of all the possible outcomes we are interested. Okay, so let's see example 2.4. So consider the sample space y, and y, and n. So I think y represent yes and represent no. So now suppose that the subset of outcomes for which at least the one camera conforms is denoted as E1. So see here, Y, 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 and Y. Okay. See, at least the one camera conforms is denoted as E1. So in the sample space, what outcomes satisfy the our interest. This is Y, 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 N. So we just choose all the outcomes containing Y, right? It's okay. So the E1 can be considered as event. So the event is such that both camera do not conform, denoted as E2, which is NN, right? And the other example of event are E3 because E2 union, E1 union E2, E1 union, you know the union, right? So union is what? You see here, E1 union E2, that's the represent the set of all the outcomes or in all the outcomes containing either E1 or E2. Okay, that's the union. And the E1 that is intersection. E1 intersected with E2. That's the set of all the outcomes belong to both E1 and E2. Okay, so E1 union E2 is nothing but what sample space. So all other examples of events gonna be what the empty set. It's called a null set or empty set. Okay, we use the symbol pi. Okay, the E4 is S, which is the sample space, and then if E5 is a Yn, Ny, Nn, then E1 union E5. What's I told you? What is this? E1 union E5, which is the set of all the outcomes belong to either E1 and E5, right? That's gonna be S sample space. E1 intersection E5. That's gonna be Yn and Ny because we just find out common outcomes belong to both E1 and E5, which is Yn, right? And then Ny, okay? And then the E1, you see that there is the prime right there. It means a complement, okay? Complement, or you just so you see a complement right here. The complement of the event in the sample space is the set of outcomes in the sample space that are not in the event. Okay, denoted by E prime or E upper C. Okay, so E1, what is the E1? E1 is Y, 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 and Y. So we're gonna find that all the outcomes in the sample space do not belong to E1, which is NN. Okay, so that's the complement of E1 or E1 complement or E1 prime. So now example 2.5. So 2.5, let me skip that example. Okay, so please the read example 2.5 by yourself. Okay, and then see we're gonna move to example 2.6. So the following table summarizes visit to emergency department at Ford Hospital in Arizona. So people may leave without being seen by a physician, and then those visits are denoted as LWBS, and then the remaining visits are serviced at the emergency department. And the visitors may or may not be admitted for a stay in the hospital. So let A denote the event that a visit is to hospital 1. Let P denote the event that result of the visit is LWBS. Okay, so and then calculate the number of outcomes in A intersection B and A complement and A union B. So now we'll see. First, we need to figure out the set A and set B. Okay, event A and event B. Okay, event A is what? The event that is visit is to hospital 1. So the set A, event A gonna be, and number of outcomes is event A gonna be 5,000. Give me a second. 5,292 right here. Okay, so this is number of outcomes event A. And the event B, let me note the event that the result. Give me a second. Oh, here. Event to denote the event that result of the visit is LWBS. So here, So we're gonna then what? Add all the number of patients in hospital 1 through 4 in LWBS, which is 953. That's the number of outcomes in the event B, right? So then we're gonna find the A intersection B. A intersection B means that what? We're gonna find out the number of patients belong to we visit the hospital 1, but in LWBS, so leave without being seen by patient, which is 195. That's the number of outcomes A intersection B, right? A complement is what? A complement number of A complement is what? All the patients who visit hospital 2 or 3 or 4, not hospital 1, right? So that's gonna be what? That's gonna be what? 22,252 minus 5,292. That's gonna be number of patient not belong to not belong to what hospital 1, right? The event A. Sorry. So and then let's see. And then A union B. A union B is what? A union B, they're gonna be the what? Set all the outcomes belong to either A or B, right? So now let's figure out A union B. So do you see that here? 5,292. That was the number of outcomes in event A, right? The number of outcomes in the event B is 953. Did we just add two numbers? No, don't do that. You see here, we have to, when you add the 953 and then 5,292, then we're gonna add, you see that 959, 195, this is the number of the patient in LWBS in hospital 1. We're gonna add that number twice. So we have to subtract. This is the what? A intersection B, right? So we have to subtract that number from the sum of two numbers, 5,292 and then 953. So you see here, the event A union B consists of the visit to hospital 1 or visit that result in LWBS or both, and contain 5,292 and then 270, 246, and 242, 6,050. You see that where that number comes from? These numbers. You see 5292 comes from the 5292 is the total number of the patient visit hospital 1, which is the number of outcomes in event A. And then 270, 246, 242 is from the what? The number of patients visit the hospital 234, but live without being seen by a patient LWBS. You see that they in here they didn't add a 195 because that 195 is already belong to that number 5292. Okay, so notice that the last result can also be calculated as this number of visit in A plus the number of visit in B minus the number of visit A in a section B. Okay, so keep in mind is when you keep figure out A union B, you have to add a number. See, so where's one? Not here. Okay. So keep in mind this when you do this you see. Give me a second. Give me a second. So when you add this one, this is A union B. Okay, A union and the B. That is equal to number of A. And the A union B, that's the number of outcomes of A union B. Okay. N of A plus N of A means N in the parenthesis A means the number of outcomes in a sample space in the event A. Okay, the number of outcomes in event B, okay, minus number of outcomes of A intersection B. A intersection B. Okay, so keep in mind this. So anyway, so let's see. All right, so now let's see. Also, we can figure out the solutions by drawing a Venn diagram. So this is a Venn diagram. So definitely two events are overlapped like this, and then the square means a sample space. Okay. So the B figure B represent the A intersection B. You see the shaded region? That's the what the that represent the outcomes belong to both A and B. Okay, and the A union B intersection B C can be figured out by that Venn diagram. See figure C. Okay, so we just say A union B. What's A union B? A union B gonna be what? Let's see. So this is A union B, right? A union B is the all the area below in the A and B, right? And then we intersection C, we're gonna find out the common area belong to both A and B, and A union B and the C, which is this. This, right? Okay. So what's the A intersection C complement? That means we find that A intersection C. A intersection C is this, right? And the complement is what? We know the flip. So all the area, the except for that area, it's gonna be A intersection C complement. Okay. And then what if a two events don't have common outcomes? Then Venn diagram can be give me a second. Venn diagram can be then this is going to be Venn diagram of the two events don't have an intersection, common outcomes. You see, so that's a mutually exclusive event. Okay, so mutually exclusive event, it means the two events denoted as E1 and E2, such that E1 intersection E2 is an empty set, is a null set. Okay, so what's the Venn diagram of the two events which are mutually exclusive? This. Okay, this. Now, next one. Complement the complement going to be just kind of back and forth. Okay, so E complement going to E. Okay, and then distributive law of for set operation imply this: A union B intersection C is equal to C. We can distribute union intersection C into A and B. So A intersection C union B intersection C. Okay, then De Morgan law. Okay, so De Morgan law is A union B prime going to be the complement can be applied to each event A and B, but the union gonna be changed to intersection. Okay, and here the intersection change gonna be that intersection will be changed to union. Keep in mind this. And then A what the A intersection B is equal to B intersection A, and the A union B is equal to B union A. So union and intersection, two operations satisfy commutative property. Okay, so keep in mind these basic property of the union and intersection. Okay, so now we move to the 2.2. Okay, so now let's see. Oh, okay. So counting technique. So now in this section, we're gonna study the um, the several way to count the possible outcomes. Okay. So in many of the examples in this chapter, it is easy to determine the number of outcomes in each event. In more complicated examples, determining the outcomes in the sample space becomes more difficult. For example, so think about this. So the so in the classroom, so there are 30 students, and then we're gonna the elect one the president, and then one vice president, and then one secretary. So then we'll figure out the what want to figure out total possible outcomes. Okay, so then how many outcomes in that sample space? This is complicated, right? So now then, so we'll see figure out this. So multiplication, first of all, we're gonna start the multiplication rule for counting technique. So assume an operation can be described as a sequence of k step, and the number of way to complete step 1 is n1, number of way to complete step is n2, and the number of way to complete step 3 is n3. And then for each way to complete step 2 and so forth, and then the total number of way to complete the operation. What that means. So back to the example what I mentioned here. So we are gonna elect the president and vice president and the secretary in the classroom. You know, there are 38 students in there. Then so the first one, the number of way to select the president is gonna be 30 because there are 30 students, right? Okay. So now then, once we the we vote the one student, okay, I mean one student elected as a president, and then for the vice president, then the number of possible outcomes for the vice president is going to be 29 because one student is already elected as a president, right? So then the vice president, the possible outcomes vice president is going to be 29. And then once we elect the one student elected as a vice president, then what's the number of students left? 28, right? Then 28 possible outcomes going to we're going to have for the secretary. Okay. So now then, what's the total number of outcomes? 30 times 29 times 30, 28. That's the multiplication rule. But what if we just select the three staff in treasury, three secretaries in a classroom? I'm sorry. I mean, what if we just? I know it's weird. Sorry, it sounds weird. But what if we just elect the? I mean, president can be vice president, and the vice president can be secretary. Okay, so one student can be charged three positions at the same time. It's allowed. I know it sounds weird. Then the number of way to select the president is going to be 30, and then for the vice president, the number of way to select the the number of I mean the what when you just select the vice president, we can also elect the president too, right? The students who already elected as president. So the number of possible outcomes for president, vice president, and then secretary are going to be 30, 30, 30 for each. So 30 times 30 times 30, which that's the total number of outcomes in that sample space. So that's the multiplication rule. So an assumed operation can be described as a sequence of k steps. So k step is for each kind of experiment, sequence of experiment, and the number of ways to complete is step 1 is n1. So number of way to step 1 is n1. There's a number of outcomes for first experiment or first step. Okay. Then number of way to complete the step 2 is n2. There's a number of outcomes for the second step. Okay. The total number of outcomes is going to be the n1 times n2 times the nk. That's the multiplication rule. So now, now let's see example 2.7. Website design. The design for a website is to consist of 4 colors, 3 fonts, and 3 positions for an image. From the multiplication rule, 4 times 3 times 3 is 36 different designs are possible. Yeah, see that? 4 colors, 3 fonts, and 3 position for an image. That was the total number of outcomes. How many combinations the designer can can make? 36. So in statistic, that's the we say that this is example of multiplication rule. Okay, and the permutation. What's the permutation? Okay, so in order to use calculation, find the number of order the sequence of the elements of set. To consider a set of elements such as S is equal to the set of A, B, and C. The permutation is a number way to what the orange, in this example, the orange, all the possible outcomes without considering considering order. Okay, so it means that, so let's think about the number way to the orange, the ABC. ABC is the ABC, ACB, BAC, BCA, CAB, and the CBA. That's the all the way to arrange the three letters ABC in the sample space S. So permutation is the number of way to arrange possible outcomes, sample space or event, depending on problem, considering order. But what's the combination two? Okay, let me explain the combination. Combination order doesn't matter. We don't consider order. So in combination is the number of way to arrange the arrange the possible outcomes without considering order. So in the view of a combination, these 1, 2, 3, 4, 5, 6 arranges permutation will be considered as just one case. Okay, keep in mind this. So the permutation, this is the number of permutations of n different elements is n factorial. So what's the exclamation mark in mathematics? That's the definition of exclamation mark. Factor is called the factorial. Okay. So now factorial is n factorial means that n times, n minus 1 times, n minus 2 times through the 1. So for example, 5 factorial is going to be 5 times 4 times 3 times 2 times 1. And then 1 factorial is going to be 1. What about 0 factorial? 0 factorial is defined by 1. Key in mind is 0 factorial is defined as 1. And then 4 factorial is what? 4 times 3 times 2 times 1. Okay. So permutation, we want to figure out the number of permutations of n different elements. That's going to be n factorial. What's the n factorial? Definition of n factorial: n times, n minus 1 times, n minus 2 times through the 1. Keep in mind that. Now then, so the next one, permutation of subset. All right, so excuse me. So number of permutations of subset of R elements selected from a set of n different elements is this. We're gonna denote it like this: P and R. What that means? P and R means number of way to select R outcomes, or we can say R object, R element, whatever, R elements out of n different elements. Okay. So for example, excuse me. So now, back to the example about the electing the president, vice president, secretary in the classroom. So 30 students right there. So we want to select the 3 students for the different position: president, vice president, and the secretary out of 30 students, right? This is a permutation problem. So we're gonna select the 3 students out of 30 students, considering order. We have to consider order. Why? Because the president, the vice president, the secretary, they are different positions. So, for example, the students A selected as the president, and the students B selected vice president is totally different from that. What in the case, students B is elected as a president, and the students A is elected as vice president. Totally different. So order matters. So selecting 3 students out of 30 students, considering order, that's a permutation problem. Okay. So that's going to be P30, n going to be 30. N is total total number of possible outcome or different element. Okay. So n going to be total number of total number of outcomes 30, and the R going to be 3. So P30R 3. That's going to be 30 times 29 times 28. So it means this. So P, and then 3, and then 3. Okay, that's going to be 30 times 29, and then 28. Okay. All right. So just keep in mind. I know. So then what's the that formula? N factorial n minus r factorial. So generalizing the that formula, it end up with that fraction. So you just memorize this n factorial over n minus r factorial, or you just memorize the way I calculate like this. Okay, starting from the total number of outcome study, and then multiply until we get what total number of the numbers is equal to that number. Okay, 30, 29, 28, and then 27. No, because how many numbers we have multiplied? 3. Stop, because that number is 3. Okay. So now next one. So example 2.8, printed circuit board. Yeah. So let me skip that example. Okay. So let's see. Please look at read this one by yourself. Okay. I told you in statistics, reading textbook is really important. So the I can't go through all the examples in textbook. Okay. So because we don't have enough time. So please read text by yourself, or so once you just sign up the willyplus.com, online website, online homework website, then you can see that e-textbook. Now here, see that video solution right there. So if you don't understand the what this example is talking about, then you can get help. We see example 2.8 printed circuit board permutation video solution right there. Okay, so look at this. So now, so next one, permutation of similar objects. So, okay, so sometimes we are interested in counting the number of ordered sequences for objects that are not all different. The following result is useful in general calculations. So, I mean, so before just looking at this, let's see example for that permutation of similar objects. So example 2.9, hospital schedule. A hospital operating room need to schedule 3 knee surgery and 2 hip surgery in a day, and we note the knee and hip surgery as a K and H respectively. So the number of possible sequences of 3 knee and the 2 hip surgery is this. 5 factorial, 2 factorial, 10. Okay, why? Okay, I'm going to explain this one later. And look at this. This is possible outcome. Just K, 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 H, H. So it's nothing but just what? This K, K, H, K, H. This is what? The finding possible outcomes is nothing but just finding the way to arrange 3 letter K into 2 H. But 3 Ks they are alike, and 2 H they are alike for each, right? So in this case, how can we the how can you figure out the total number of way to arrange 3K and 2H? 3Ks alike and 2H alike, right? So in that case, order matter? Yes, order matter because K and H, KH, HK different, but not all 5 elements are different. Only two group group A and group H are different, right? In that case, we use the permutation of similar object. So number of permutations of n can be um, the can be grouped as n1 through the nr. Okay, so n1 is, for example, in this case, in that example 2.9, n is 5, and the n1 is 3, n2 is h. So n1 is a number of k, n2 is a number of h. So we're just grouping. Okay, so by the grouping, we got this. 5 is equal to 3 plus 2. So n1 is number of k, n2 is number of h. Then observe which n1 are one type and n2 are the second type, and so on and so on. Then the number of total number of ways to arrange 5 elements. Okay, that's going to be n factorial divided by n1 factorial times n2 factorial to the nr factorial. In this case, r is 2. R is a number of groups. Okay, or number of types in general. Okay, so example 2.9, how many groups? 2. R equals 2. So n1, we need to figure out n1 and n2. n1 3, n2 is what? 2. N1 is 3, n2 is 2. And how many outcomes or how many surgeries in a day? 5. N is 5, right? So 5 factorial divided by 2 factorial times 3 factorial going to be 10. Really? So now let's see. Let's figure out how to calculate this. The factorial. Okay, give me a second. Okay, so 5 factorial times 2 factorial times 3 factorial, right? So this is equal to 5 factorial is what? 5 times 4 times 3 times 2 times 1. But 3 times 2 times 1 can be expressed as 3 factorial, right? Divide by. Okay, so give me a second. So now, and then 2 factorial, I just copy 2 factorial and then 3 factorial. Okay. So now you see that 3 factorial, 3 factorial cancel them out. So in 2 factorial is nothing but what? 2 times 1, which is 2. So we got 5 times 4 divided by 2, which is what? 10. Okay. Or when you go to using TI-80 4 plus, so I told you we're gonna use TI-83 or TI-84 or TI-84 plus calculator in the lab. Okay, so keep in mind this, so you need to get it. So in the 5 what? So in the press the map here, and then go to the, let's see. Oh, oh yeah, so I'm sorry. So here, then you can calculate the you see the NPR right there, and then NCR. The NPL is the permutation, okay, number of way to select the R elements out of n elements considering order, which is permutation, and NCR is combination, and then you see factorial right there. Okay, so I press the math button and then go to the probability. Okay, then you see the NPR, NCR, and the factorial. You see. Okay, so now let's see. Okay, but 2 point. We did 2 point. Okay, now is the combination. Okay. All right. So combination. Another counting problem of interest is the number of subsets of R elements that can be selected from a set of n elements. So here, order is not important. These are called the combination. So every subset of R elements can be indicated by listing the element in the set and then marking each element with the star, or say asterisk, right? Let me say just star, okay? If it is to be included in the subset. Therefore, each permutation of R star and n minus R blanks indicate a different subset. What's talking about is, is confused, right? Let's see example. So for example, if the set is S, sample space A has A, B, C, D, 4 element outcomes there, the subset A and C can be indicated as this, like this. Now, the number of combinations subset of R element that can be selected from a set of n element is denoted by, see, the n or n combination R, or NCR, or like this, C upper n lower R. Okay. So NCR, how can you calculate NCR? NCR is actually we calculate NPR and the divide by R factorial because, again, let's see. So NCR, or let's see, let's follow the notation what textbook use. This one is nothing but NPR divided by R factorial. How come? Give me a second. So because when you calculate NPR, we consider order. How many elements we consider order? R element. We consider the order of R element, right? So when we divide the R factorial, which is the R factorial is the number of outcomes we got when we did consider the order of R element. So we divide by R element, R factorial, then we're gonna get the number of way to select R element out of n different element without considering order, which is combination NCR. Okay, so that's it turns out that this is the by the way, the notation of this one is n, or sometimes you use this one. Okay, it's nothing but what's the formula of NPR? This is n factorial divided by n minus r factorial, right? And then divided by r factorial. So now this is equal to what? This is n factorial divided by the r factorial, oops, r factorial divided by n minus r factorial. Okay, that's what we got that. Sorry, we got the that formulas. Okay, so now give me a second. So example 2.10 and let's see 2.11. So please read look at the examples by yourself. Okay, so the I just covered 2.1 and 2.2. Okay, in this video. So next time I'm going to cover 2.3 and 2.4. Okay, so let me stop here.